Thank you very much. Thank you, Dr. Joholi, for the introduction, and thank you for the opportunity here. Today, I'm going to focus on the topic of AI, specifically in the air interface and in the RAN. Somewhat of a narrower scope from an overarching, telecommunication standards point of view. I promise you, I do not have a spider chart or a 3GPP timeline. Moving on, so we all have heard about AI, and it's all around us. It's good to kind of take a step back and understand why. What is artificial intelligence first? We started off in the very early days with this so-called Turing test, whether you can basically distinguish whether a man or a machine is asking you some questions. I think we are way beyond the Turing test now. We are in the realm of understanding and deciding whether an artificially intelligent system needs to be thinking humanly or thinking rationally, or both. Sometimes they are mutually exclusive, as you all know. Humans do not always think rationally. And again, once having thought through a problem, whether the action from the AI engine is again rational or not, these are all very large-scale moral, ethical questions even that the entire world is struggling with. And you will see governments of the world getting involved in setting policy in these areas. But why is AI so important? We think that it is a technology of the order of, say, the transistor or of internet search. Right? It will scale many orders of magnitude and disrupt many industries, and including ours. And it is so important because it opens up technology to a very broad variety of people of various skill levels to be able to access the best of technology and also to create the best of technology. One more thing it's doing successfully recently is that it's making the most important coding language being just human spoken language, perhaps. Economists are predicting that the AI will add trillions of dollars to the global economy as a whole. So we better pay attention to it from the telecommunications world as well. So just another brief view at what is the state of the art today in AI. And the material is from a really excellent report by Stanford University that came out this year. We all know about facial recognition. It now works with almost 100% accuracy. We all breeze through immigration lines and boarding gates and so on and so forth. But at the same time, it's also a measure or a tool for surveillance. Then on the flip side, the problem of areas like deep fake image creation and video creation are coming to plague us from the AI world as well. Moving from just sort of the raw video world, there is also visual reasoning where the computer or the artificial intelligence engine is able to ask and answer fairly involved questions about images and videos that are being shown to it. Then moving to the text and language area, text generation has recently become really the bane of all the middle school and high school teachers in the world, because whatever question they assign, they're not sure anymore if the answers are coming from the students. The capabilities are exploding on a daily basis, as we can see. Again, translation models as well have grown. Beyond just the artificial intelligence algorithms world, there is a parallel rise of the GPU, or generally the computing hardware that enables AI, because without that, a lot of these things will not have been possible. There have been dramatic improvements in size and also performance and cost, and a more recent sort of perpetuating development has been the use of AI in order to develop better GPUs and hence providing better AI. So these are all sort of the developments in artificial intelligence that are coming to our industry as well that we have to really pay attention to and utilize as opportunity. So what is this going to do for AI, especially in the radio access network and air interface? On the left side of this slide, we see what we call a human-designed communication stack, traditional physical layer modulation and corresponding receiver operations, and a traditional MAC layer with some kind of a scheduler, some kind of a beam management, and so on and so forth. Then followed by some multicellular radio resource management, or what we used to call self-organizing networks, mobility management, and so on and so forth, all run through traditional communication theory educated or informed algorithms and implementations. And then on the right side, we have this new beast, which is this AI-powered transceiver or radio access network, where the ultimate goal is to have a completely dynamic AI-native air interface, to have federated and edge AI models for running almost all of the MAC functions, like the scheduler, like the beam management. And then moving further up, using AI techniques to do all of the things that we, or many of the things that we traditionally have done through other means, like security management, energy management, mobility management, so on and so forth. And of course, at the application layer, it's not just us, the telecommunication industry, but the entire ICT industry as a whole that's contributing to the application layer. And so really, the level of innovation is, the sky is the limit. Beyond just the running of the RAN network, there is also the life cycle management. How do you plan the network? How do you deploy the network? How do you keep it operational? How do you manage faults? And all of those are slowly being taken over, or at least that's the promise, that AI will be able to do all of these functions with superior capabilities compared to the past. So this is the promise. Now, digging a little bit deeper into the air interface, again, the evolution has been that we have a human-designed transmitter and receiver with the normal sort of encoding modulation functions of the transmitter and the corresponding equalizer, estimator, decoder at the receiver. Now, the first step in moving towards AI has been the experimentation of, or the replacement of individual modules on the receiver with AI. And these are possible in isolation because these do not have to be standardized. These can be proprietary implementations, and hence there is a lot more scope for sort of individual innovation here, and that is certainly going on as we speak. The next step, again, sort of in a manner that is individual and not requiring standard specification, whether multiple of these elements and blocks can be put together, and can you come up with many more, much more highly optimized form of receivers in a way that you could not do in the past simply due to the complexity of the joint optimization function. And that is also going on right now. But slowly we are moving into sort of the standardized AI in the air interface. We already see some use cases being talked about in 3GPP, but moving towards 6G, can we do a joint, completely dynamic AI native transceiver, which is able to instantaneously recognize the channel and optimize the modulation and coding scheme in an arbitrary way, not relying on just this modulation alphabet that we have of the MCS schemes. Going beyond that, can we do better than that? That's kind of the holy grail, and that's where the industry has ambition to head towards. Whether we get there, I think that's the question we all have to ask ourselves. So just to elaborate a little more, we have the influx of AI into almost all of these blocks. Right? You could have AI-based modulation and coding. You can have even AI-driven DPD, for example. And you can have AI-based spectrum sharing techniques moving a little bit higher into the RAN, and similarly energy optimization and scheduling. And of course, AI-based CSI feedback we all know about. That's currently a work item, or it's a study item in the 3GPP world. And beyond that, of course, the notion of signal analysis opens up once you throw artificial intelligence into the mixture. So all of this, as the previous speaker mentioned, requires cooperation in a very real way. As we know, we can start off in our own isolated, worlds in, optimizing functions that belong to ourselves. But in order to really truly reach the promise of a dynamic air interface and RAN, you would have to have cooperation across the board in enabling, the sort of two-way AI that has to be a cooperation between the transmitter and the receiver, that is the G node B elements and the UA elements, and perhaps other elements of the network in conjunction with the G node B elements as well. So a lot of collaboration and cooperation is necessary in this area. And one more thing here I would like to mention is also the channel model itself. So the traditional stochastic channel models in 3GPP have been fine, have been okay overall in terms of providing a view of the relative performance of various different mechanisms and algorithms and coming to a decision. But we are moving to the need to have extremely precise channel knowledge for the purpose of directivity, for the purpose of spatial multiplexing, but also for the purpose of providing a very high level of confidence in the functioning of the network, whether it is an indoor factory floor where a robot has to move with 100% precision, or any of the other use cases you can think of outside as well that require that kind of precision. So we are slowly moving into this very ultra-precise channel modeling, and we believe that AI will play a role in that as well. So talking about this collaboration, Charlie mentioned in the previous talk, we were very honored to have collaborated with Samsung in creating a framework to demonstrate this AI-based CSI compression, and not just demonstrate, but to be able to study the impact of various configuration parameters and so on and so forth. Just very briefly, we all know that in conventional sort of the current 3GPP methodology, the CSI information is encoded in some fixed format channel feedback that you can pre-select. And that gives you the ability to convey rank, MCS and precoder information. Now, the new AI-based CSI compression provides the ability to use AI to sort of vary the kind of encoding that is done at the UE for the channel, so that you can put more energy or more precision into areas of the channel which have more to give. Especially if you take a very large bandwidth channel with high frequency selectivity, this kind of mechanism really helps. And that was what was studied here. We were able to do this sort of in real time with our channel emulator in the middle, as well as our test automation framework that provides kind of the glue where all of this comes together. And you saw some results in the previous presentation as well. So moving on to AI/ML, beyond the air interface into the network, the one important development has been this notion of the RAN intelligence controller in ORAN. It is not that such techniques are not possible without a RIC, but that the RIC has enabled and provided an interface and a mechanism for many more players to try and innovate in these optimization applications, which can then be utilized by the network. So it almost provides an app store for network optimization techniques. And what are the type of techniques? We have seen, right now, energy efficiency is kind of right at the top in terms of what people are experimenting with. Then we have mobility, handover, and so on. Eventually, we are still in the 5G and 5G advanced. What will emerge as the optimization methodologies required for 6G? I think we will know as we move forward. All the great new use cases that are being experimented or being postulated for 6G, like sensing, joint communication and sensing, like intelligent reflective surfaces and so on, all of them will have some form of optimization associated with them. Beyond the sort of RAN performance, there is an element of security that has to be paramount. So AI can be utilized in combating or providing security to the network, but AI in itself brings certain security implications and risks that have to be tackled, like data poisoning. And we expect these to be very important aspects going forward. So I'll skip this in the interest of time. We all know the current 3GPP status on this. Again, I think I'd like to move on to the one final aspect, which is that the introduction of AI into the network has a lot of implications on how you test the network, how you measure performance of the network, and how you verify that the network is going to operate in a stable and resilient way. In the past, and this is obviously of key importance to a company like Keysight. We boast, we are proud to be sort of the world leaders in the test and measurement world until now. AI brings a new challenge that we have to master. We are traditionally doing things like compliance to the specification, testing interoperability, testing performance. But AI brings a new set of challenges. We are going to have to test things like stability and resilience in a new way. Explainability is a very key ingredient of AI test and verification. And the whole notion of the sufficiency of data for training and so on. All of these are going to be very important aspects that we have to think about. One thing I'd like to mention is, Dr. Geoffrey Hinton, who was with Google, considered a pioneer in the field of AI. He made a statement that at the moment, 99% of the resources are being used to build AI, and less than 1% to test AI, and that, in his opinion, it should be 50-50. So we have a way to go to get there. The last slide from me, what are some of the challenges for AI/ML in the RAN? I think we do need to get beyond the hype cycle. We are, I think, in the middle of it. To understand what are truly the core set of applications where AI will be important and where perhaps the performance will not be matching up to the level of complexity and effort needed. Now, the flip side is, for innovating in AI, the lack of data is a big hurdle, especially for the sort of the smaller entities and universities and academia. And I think the community as a whole will benefit by enabling these entities and providing the data. I already mentioned cooperation across the industry. and interworking mechanisms need to be established. And finally, the lack of well-described and well-understood test methodology, I think, is going to be a key hurdle that we all have to cross. In ORAN, we've made a beginning, and in some other bodies as well. There has been discussions in terms of what the test methodology should be, or what are the core principles behind them should be, and looking forward to contributions from the entire industry in making this a success. So that's my talk. Thank you.